I can easily write K2, K1. Right? Now how do I get this? I need to evaluate B and A for reflectivity and C and A for transmission. I have these equations over here. Psi 1 I know, psi 2 I know. I do not know the ABCs yet. But I have one boundary condition. And that's not exactly a boundary condition in terms of confinement, but the boundary condition says that at x equals 0, the wave function must be well behaved. That is, psi 1 should be equal to psi 2. If I put that, then A plus B comes out to be C. Yes? And also another condition for well behaved wave function was that the first derivative be continuous. Yes? That would give me A ik1 e to the power ik1x. So that's 1. So ik1 into A minus ik1 into B should be equal to ik2 into C. And then I can get rid of the I. So K1 into A minus B would be equal to K2 times C. Now I have three unknowns, A, B and C. Two equations, K1 and K2 are known. I know the potential. So I have three unknowns, two equations. I can always write B in terms of A or C in terms of A, which means I can get my ratios. And solving that, what I'll get, let me write that, the reflection comes out to be K1 minus K2 by K1 plus K2 square, and transmittance comes out to be, well, it's 1 minus reflection, right? It is 4 K1 K2 by K1 plus K2 square. Okay. If on the other hand, so this is something which is different from classical mechanics straight away. Yes?
You said you had two equations, but given that R plus T is equal to 1, what we have three equations?
That's R plus T equals 1.
And R and T can the result come from K, B, C,
So is it a, do I get a independent equation or it's a dependent equation? Okay, if it's an independent equation, you could solve. But normally what you do is to get the value, if you have these two equations, right? You can get everything in terms of A. And finally you normalize the wave function and get the value of A. That's the way you normally do all these things. So, now what if E was less than 0, V naught? Concentrate on the fact, what would be K2 now? K2 would be root 2m E minus V naught by H cross, right? E minus V naught is a negative number. So I can write this K2 as K2 is equal to I times K2 prime something, right? And then I put it back in the solution. So the solution was C E, again we don't have any counterpart from the right, it's only going to the right. C e to the power, it was I times K2x, right? So I times I K2 prime x, where K2 prime is a real number, right? C e to the power, so this will be psi 2. Sorry. Minus k2 prime x. Right? That shows that the wave is on an exponential decay. Yes? What is going to happen is that I have my A incoming wave. I also have my B. Let me try to draw it with the smaller amplitude but same frequency. And I don't think I'll be able to do it. So let me draw the same thing with the smaller amplitude. That's what would be represented by B. Now it cannot go over the top definitely because it has lower energy. But what it does do is it decays into this exponentially. Okay. Now you'll ask me, how do you know this for certain? I don't know. Yeah, if it decays, it dies inside. I just don't know. Perhaps I could get my reflection coefficient. Right? There's no transmission. Another thing that I wish to mention over here, if you look at this wave equation, it's e to the power minus k2 prime x. If we go back to our first lecture where I said that we had these three solutions, k equals 0, k less than 0 and k greater than, and I said k greater than 0 is a subset of k less than 0. So k greater than 0 gave you a kind of an equation that was, well, essentially d squared psi by dx square plus 2m e by h cross minus v naught psi equals 0. This is what our Schrodinger equation is like, right? When E minus V naught is negative, that is E is less than V naught, then I get this particular case. You know, let me remind you, we had put capital K is equal to K square and capital K is equal to minus K square in another case. In this case, we had put it equal to K square when K is greater than 0, and this was for K less than 0. So now this is the case exactly. Yes? And the solutions that I am getting are e to the power minus k2 prime x. So in general, the solutions that I will get would be a e to the power minus kx plus b e to the power positive kx. Okay, and you have to interpret that physically. So the psi in this case would be exactly a subset of k less than 0 that you see. The psi in this case would be an exponential decay or an exponential rise, but you know, things don't happen automatically. You just don't pump in energy into the system without any cause. So this is rather the case when x is less than 0. So it's an exponential decay in the negative side. In the present case, we had a barrier at x equals 0 in the positive side. So that's the equation that we get, c e to the power minus k2 prime x. Okay. Now, you would tell me that how do you know that this wave has decayed into this box, into this potential step? So what I'll do is, I'll make this potential step small. No, not in height, but in width. So I have this region 1 and region 3 which are exactly identical. And here I have a potential barrier between 0 to L, let's say. Let me just check if I've used the same thing in my notes. Well, it doesn't matter, I think. Mm. It's A over here, but it doesn't matter. Anyway, we are not going to solve this. It's a very complicated solution. I'm just going to qualitatively describe it. Now, what's going to happen over here is that you had the incoming wave, and then I had an exponential decay in this region. So I'll have an exponential decay over here, and then if I observe, so I know how much the decay would be, e to the power minus kx, and then in region 3, if I again observe the wave with a reduced amplitude but the same frequency as in region 1, because region 1 and 3 k is equal to, or k1 is equal to root 2 me by h cross. In region 2, it's k2 prime that we wish to use, then it's root 2 m v naught minus e by h cross. Or if you want to say k2, then you can write t minus v naught. It's going to decay like that. And then again, I have two boundaries, 0 and L. Yes? So I have to match psi 1 and psi 2 at the boundary condition. I have to match. So psi 1 equals psi 2 at x equals 0. Psi 1 prime equals psi 2 prime at x equals 0.